to have Pavel Mozolyako from St. Petersburg State University, and before then in many other places. We'll be talking about a Hardy operator on the bitree and some unexpected combinatorial properties of planar measures.
All right, thank you so much, Nicola. Thank you, Filippo, for having me here. Thank you guys for attending this seminar of mine. So this is something I gave quite a few talks in the last couple of years, and this whole thing started with, well, you see the names, but of course with Nicola here. So he would be the one who introduced me to this whole business. Okay, and also, I kind of would like to apologize in advance because that's pretty much my first experience of giving a talk in Teams. So I'm logged in with two devices here. I talk into my laptop and I'm trying to write stuff on my tablet. So it can happen that one of them, or maybe both of them, will log out. So please be patient with that. All right, so as Nicola said, this would be about Hardy operator on the bitree and some unexpected combinatorial properties of planar measures, mostly. But first of all, of course, I would like to give a shortish introduction to this whole business and to describe what's actually happening. So as you see, it's a joint work with Nicola, Sasha Wolberg, and Pavel Mozolyako and some other people, because the list is, well, somewhat extensive, and I guess I only had 4 slots, 3 slots to use. Yeah, so let's start with a plan of sorts. Hopefully you can see it here. The main motivation was, of course, came from the study of the Dirichlet spaces of analytic functions on the unit disk. Somewhere along the way, we found out that there could be another motivation, which is about actually a continuous Hardy operator on the real line and on the plane. But okay, the original thing, of course, came from the Dirichlet spaces. All the necessary definitions will be given along the way, and so long as that, I will describe the problem, the thing we have started with. I will say a few words about the Hardy, the classical Hardy operator on the real line and then on the plane, and then I will say something about something that corresponds to the actual title, about the discrete model, and on the tree and on the bitree, and what is known, what is not known, and what problems we are encountering right now. Also, I would like to mention that this is absolutely a work in progress, so we know a few things, we don't know many more things, and yeah, there are some problems here that's actually quite funny, in my opinion. All right, so, okay, again, sorry. So the originating point of this whole thing would be the Dirichlet, in this case unweighted Dirichlet space on the unit disk, which is, I guess it's the best way to define it like this. So you have a unit disk on the complex plane and you consider analytic functions in the said disk which admit the following representation. So basically this one. And the norm, it is a Hardy-Sobolev space of analytic functions, of course, and the norm is given in the following way. So you have a certain parameter A here, and for the case when A is 0, of course you get the most classical Hardy space on the unit disk. When A is 1, you get another classical thing, a Dirichlet space. I think if I'm not lying, that would be the more convenient way to write the norm here. And when A is smaller than 1, so smaller than 0, you get Bergman spaces, and when A is greater than 1, you have the spaces are not really interesting. So you have the classical Bergman-Hardy Dirichlet scale, and the two usual cases we will be considering would be what I like to call them the endpoints of the scale. So the Hardy case when A is 0 again, and the Dirichlet case when A is 1, and everything in between. Okay, so of course, the theory of one particular brand of problems, which Nicola told me about and that we were considering. This would be the problem of describing Carlson measures for this space. So since I start with a one-dimensional scenario, I guess everything is already known or was already known by about 1980, I guess. Well, the whole thing was done by Stegenga. So basically, he described the Carlson measures for the classical and the weighted Dirichlet spaces on the unit disk in terms of some capacity, which is naturally attached to the corresponding space. I mean, if you have a Hardy-Sobolev space, you have by the law of nature some kind of capacity attached to it, and that would be the instrument to describe the whole thing. So to give a few definitions of the object I'm actually going to work with, and yeah, I have to apologize just now because apparently my tablet is lagging quite a lot. So yeah, the screen should be moving. Right. So what the Carlson measures are about, the most general definition, I guess, would be this. So if you have a Hilbert space of analytic functions on some domain omega in the complex plane, then you can consider the embeddings of that space into some L2 space, usually on the closure of omega, with respect to some measure mu. And if this particular embedding is bounded, then this measure is called the Carlson measure for that space H. So the classical result here is the so-called one-dimensional theorem, which is actually a collection of a bunch of theorems, namely, mostly by Stegenga and Carlson. Okay, so first of all, of course, it started with the Carlson theorem about, eponymous measures for the Hardy spaces, and then it was done for Bergman spaces by Lukin and for weighted Dirichlet by Stegenga. So I try to unify all these theorems into just one statement, hence quote theorem unquote. And it goes exactly like this. So let F be from one of those weighted Dirichlet spaces with this particular norm here. Then the measure mu is Carlson for that space. If and only if something like this happens. So some inequality of this type, where the quantity kappa alpha, the function kappa alpha, is different changes when you change the parameter a. That is for a is 0. That is for the Hardy space case. This kappa alpha is just the Lebesgue measure of whatever we have on the right hand side. And for a is greater than 0, for a is 1 for the Dirichlet space case. And this is just the logarithmic capacity. Well, Bessel one-half capacity, which can be obtained from the logarithmic capacity. Maybe use the word logarithmic somewhat incorrectly here because you have to take logarithm of that, but nonetheless, let's call it logarithmic capacity. And for a between 0 and 1, you again have some kind of Bessel capacity which is attached to the corresponding weighted Dirichlet space. All right. So again, I would like to mention that what are you measuring actually? So you take up any finite collection of disjoint intervals on the unit circle here, and this is just the union of those intervals, and this is the union of tenths over those intervals. I think I have a picture somewhere close by. Yeah, I do have a picture. So if you have an interval, you just cook up a tenth over this interval. So this is a curvilinear rectangle, an oxymoron of sorts, but nonetheless. And the length of the side is proportional to, let's say, length of I2 divided by, say, 2 pi. So this is the tenth attached to the rectangle. So going back to the formulation to the guy here, you have the union of those tents, and the measure of any such union must be dominated by this kappa A taken of the union of said disjoint intervals. Again, if A is 0, so if kappa is just the Lebesgue measure, then the condition of having a finite collection of disjoint intervals can be split to just checking it on a single interval, because Lebesgue measure is additive. And these guys, the tens by construction are also disjoint. So since everything is additive, you can just check this condition on just one singular interval. However, if kappa A is some kind of capacity, then pretty much in all cases the capacity is not additive. At best, it would be subadditive. So, for instance, for the Dirichlet case, you kind of have to apply this kappa, well, this logarithmic Bessel, whatever capacity, to the union of any finite collection of disjoint intervals here. So this is important. All right. Another way, just to say a few more things about this condition, even for the Dirichlet case, the capacity, be it a Bessel or logarithmic one, is the thing that is not that easy to compute usually. So for reasonable sets like an interval or whatever, this is something computable. However, if you have just a random collection of disjoint intervals, yeah, the capacity of those, well, basically you don't have any kind of reasonable formula. So by nature, it's sometimes better to get a somewhat of a more geometric description here, and this is exactly what this theorem tells you. And again, this can be this have a nice correspondence for the known results in the Hardy space. So again, this is something very well known. So for the Dirichlet case, of course, and this tells you that if you have a positive measure on the unit disk, then it is Carlson for the Dirichlet case, for the Dirichlet space, unweighted one, because it's more convenient to state it only for unweighted case. If this geometric, I call it local charge energy condition, happens. In particular, if okay, possibly I should write the closure of the disk here. In particular, if the measure is supported on the unit circle, which in the Dirichlet case is more or less natural thing, because if you are, by again some law of nature, if you are looking at the Carlson measures for the Dirichlet space, you can sweep them to the boundary due to by some canonical way. Then you have a very nice condition here, which tells you basically, so if you have, let's say, your measure mu, which is on the boundary, on the unit circle, must be subject to this kind of geometrical condition. So you fix any dyadic interval here, and consider the family of all of its dyadic subintervals. So let me write this possibly, if I write this in the tree form. So you have a dyadic interval, you have a couple with subintervals. Okay, this. So this would be I, and this would be in J. The family of dyadic subintervals. So the sum of all squares of all these dyadic subintervals of mu of squares of the masses of all dyadic subintervals should be dominated by mu of I. This is an if and only if condition. And similar conditions with some weights, of course, hold when you live in the unweighted Dirichlet space. In particular, again, if you compare this with the famous, well, the classical Carlson theorem for the Hardy space, you see that you have a similar condition, but instead of sum of squares, you just take the measure of the tent. So this condition is slightly more linear. Right. So yeah, let me skip the picture. So this was the motivational part that comes from the Dirichlet space, and there is another one which is on the first glance quite different, but then these two lines of thinking, they kind of converge at the end, which I hope I will have the time to tell you about. So let me get with that real quick. So this is, again, the first glance, this is a different problem, but turns out to be pretty much the same. So you do the Hardy operator on the real line. So let us define a couple of operators which are applied to some function, let's say non-negative function. I don't require it to be summable or anything because it will be by our considerations. So the direct operator is when I integrate from 0 to x, and the adjoint of ish, quote unquote, is when I integrate from x to plus infinity. So usually function f is supposed to be integrable or whatever. Not that much of an important condition. So then I consider the two-weighted embedding here. So I have a couple of weights mu and v, and I have different p's and q's like that. And I'm asking when the guy on the left-hand side is dominated by the guy on the right-hand side, when p, q, mu, and v are given. So this was a question, well, a very classical question. It was answered by 50-something, actually almost 60 years ago in different papers. And the condition for such an embedding to happen is, of course, this one. So the supremum of these guys should be finite, and this constant here is actually proportional to constant here. And W is what you get from the weight V when you do the usual dual thing here. So this is formulated for any P and Q, and from now on I just want to forget about nonlinear cases and get to the linear case, because even the linear case is quite an interesting thing, in my opinion, especially in higher dimensions. So with that in mind, I will try to do the same thing that I outlined here, but in the discrete setting. So you can imagine the real line to be quite an analog of the positive integers, right? So instead of real line, what I will be considering positive integers here. And I will move all the scheme from the previous slide to the positive integers by saying, okay, now I have function which is defined on positive integers, and I will consider these two operators here, which naturally are direct analogs of what I had on the previous slide. So this is the integral from 0 to n, this is just the integral from n to infinity. And since I put p to be q to be 2, the corresponding embedding with weights, now the weights are on positive integers as well. On natural numbers, 1 plus 0. The corresponding embedding now looks like this thing, and the condition, again, in the linear case, is just this thing here. And the constant here, is, of course, is proportional to that constant there. So that's how you do when you want to discretize this whole thing here. But there is a way, maybe not immediately obvious, but there is a way to get to this particular problem from a slightly different viewpoint, namely, I first of all, I will give slightly different notation here. So I'm still on the natural numbers, but now I look at the natural numbers as a directed graph. So I have a root which is at 0, and I have a bunch of vertices. So this will be 1, 2, 3, 4, etc. And I denote these vertices by Greek letters, beta, alpha, gamma, and whatever comes to mind. And then I define pretty much the same operators here. Okay, so maybe I have a little bit of a confusing thing, because I write alpha is smaller than beta if alpha is greater or equal than beta as an integer number. So when I say this is alpha and this is beta, in this case, alpha will actually be greater than beta, which is counterintuitive, but this works better with the graph theory. So I just do the whole thing which was done on the previous slide, but with a different notation here. So I guess this would still be the integral from 0 to alpha. This is the integral from alpha to infinity. And again, these are, well, this is the direct embedding. And this is the dual version of the direct embedding, because of course, if you have the Hilbert case, of course, you can move anything to the dual scenario. So this is just, again, the natural numbers, but with a different notation. So I will keep now this notation in mind, and I will move to a slightly more general situation that is of a dyadic tree. So consider now a rooted dyadic tree, encoded by the dyadic subintervals of 0, 1 ordered by inclusion, which is the most classical thing. So if you look at the previous real line, now I will turn it by 90 degrees clockwise, and I will, since I can consider the natural numbers plus 0 as a graph, I will say, so this is the root, and this is a directed graph here. And as you can see, this is also a tree. It is not a dyadic tree, of course, because every vertex has just one child, but it is a subtree of a dyadic tree. So when we are considering dyadic tree, actually, this means that we add a bit extra. So that means that we actually have this. Okay. And here you have, so basically, it is a very, very small subtree of a natural dyadic tree. So we can start doing the same thing and define the analogous operators. Now I'm using the dyadic intervals notation. And again, consider the corresponding embeddings. And it turns out, this is an inequality due to many people. So for instance, this can be viewed as a corollary of some theorems by Nazarov, Trell-Wolberg, or by Nicola Rohberg, Sawyer, and Wick, to the best of my knowledge, that the necessary sufficient condition for this embedding to happen is a single box test with respect to the pair of weights W and mu for any dyadic interval Q. And you can actually weaken this condition and obtain this inequality here when you leave on the dyadic tree. So this is something very much combinatoric, and you can get to this particular problem, well, for instance, from the direction of the continuous Hardy operator on the real line. So you take real line, you discretize it, and then you add a bunch of branches, and you get a similar problem. However, the dyadic tree representation we actually considered it just due to the fact that we wanted to study the unweighted Dirichlet spaces, well, on the bi-disk, but on the unidisk first. So there are many ways in which you arrive to this particular scenario here. So, okay, that would be a picture that I will skip. And this would be a sort of an explanation why do we do this. So the dyadic tree setting is a nice model for weighted Dirichlet embeddings and the Hardy operators on the line. So we take two starting points and somehow they converge to some discrete model that covers them both quite nicely. So in the Dirichlet case, we just use the Whitney decomposition of the disk, and then by some magic stuff happens with this particular weight. And the Hardy operator on the real line, you do just what I told you, that we just observe that Z plus is a subgraph of the dyadic tree. So just by putting the weight W to be 0 on all vertices except one chain, one branch, you can get the model for Z plus and henceforth for the real line. So this is that was known. Maybe it was not explicitly stated, but this all the results that I stated that I mentioned here were known, and this on that form. And now I can say finally that what our real motivation was. It was, of course, to try to increase the dimension in the analytic case. Namely, we wanted to consider the Sobolev embeddings, the Carlson embeddings of the Dirichlet space on the bi-disk. And henceforth, the two-dimensional or polydimensional versions of the tree had to appear naturally. Okay, so let me skip this picture. This is the Whitney decomposition of the unit disk. So let me say a few words about the Dirichlet space on the bi-disk, because that's the object that I will try to consider. And as before, well, so now as the underlying space is the bi-disk, which is the Cartesian product of two unit disks in C squared. So you now consider the functions of two complex variables, z and w, which can be represented as these polynomials, and in the very much the same vein, the unweighted Dirichlet space on the bi-disk can be defined like this. So you just take the one-dimensional definition and you just add extra indices here. So this, let me put one here and one here, which somehow says that I rise to the power 1. An equivalent definition, if you want, the direct definition with all the partial derivatives is here. It's quite inconvenient to use, so let's just forget about this altogether and just concentrate on this one here. So again, as before, there is a weighted version when I rise not to the power 1, but to the power a and b. So this would be weighted. Okay, I'm sorry. Again, my tablet is lagging, so I will have. Yeah, it is. So I can again define the weighted Dirichlet space by rising to slightly different powers a and b here, and I can try to imagine what would the Carlson embedding theorem for this new space look like. And this is exactly what the title is supposed to say, the suggestion for the general two-dimensional theorem, which is basically, again, the direct analog of one-dimensional fact. I just add a bunch of new indices here. So the suggestion goes like this. Again, you have some quantity kappa, some function kappa, which depends on a and b. I will not specify yet how it does depend on these two parameters. And I fix any finite collections, any couple of finite collections of intervals ik and jk, well, the same number of intervals on each coordinate circle. So, and I would like that it would happen so that the measure mu is Carlson for this weighted space if and only I take the measure of the product now, because the measure should live on the bi-disk, of the product of tens, of the union of product of tens. It should be dominated by this quantity kappa taken applied to the union of product of the bases of those tens. So basically you take one-dimensional theorem and put the Cartesian product everywhere. So, and again, by suggestion, for the Hardy space on the bi-disk, this kappa should be the Lebesgue measure, now two-dimensional Lebesgue measure. And for A is B is 1, so for unweighted Dirichlet space case, this should be the two-dimensional version of the classical 1/2 Bessel capacity, which is now 1/2 Bessel capacity, or by logarithmic capacity. So again, I will not define this particular capacity here, but again, you just take one-dimensional object and plug in the extra dimension there. So instead of, say, logarithmic kernel, logarithm of z minus y, z minus w, you take logarithm of z1 minus w1 times logarithm of z2 minus w2. And then you get the bilogarithmic kernel capacity, for instance. So this, while it is written as a statement, this is not a statement. This is what we hope is happening. And turns out that for some, well, our main result is that this statement is indeed true for some selected values of parameters a and b. So let me, okay. So let me move a few slides lower. Okay, yeah. So let me first of all give you a little bit of a lie. So there is a theorem by Ellis Chang and Robert Pfefferman from 1980s, early 80s, that the measure mu on the bi-disk is Carlson for the Hardy space, that is for A is B is 0, if and only if for any finite collection of rectangles, and the rectangle is of course ik times ik times the measure of the tents taken above these rectangles is bounded by some constant times the two-dimensional Lebesgue measures taken of those rectangles. So the funny thing is that as it is written, this statement is a lie. And to make it correct, here I will have to add H2 harmonic, well, biharmonic. Which means that this particular version of the Hardy space for the bi-disk consists not only of analytical functions on the bi-disk, that is, of the functions with Fourier coefficients which lie in the upper right quadrant, but of all functions. So you take an L2, any L2 function on the torus, which is the distinguished boundary on the bi-disk, and then you extend it inside harmonically, and then you get H2 biharmonic on the bi-disk. Then if I write this particular biharmonic index here, then this theorem would be correct. And this is known. The funny thing is that we don't know really. This would be the one funny problem that I have no idea. Well, I have some idea, but I really cannot state if it works or not. If we can replace biharmonic with the proper analytic case. Because again, so let me go back to the definition of the weighted Dirichlet space, or for the Hardy case. So when A is B is 0. You see, I consider here only the positive, the upper right quadrant. So if you look at the Fourier coefficients of this function, you see that it lives, they live only in here. So that would net you the sum of squares of these coefficients, and that would net the classical analytic H2 on the bi-disk. However, you can consider coefficients that live on the whole Z2. So for instance, coefficients here, coefficients here, coefficients here, and coefficients here. And okay, again, unfortunately my tablet is lagging a bit, so the picture will appear at some point. Right, so the thing is that, right, it is lagging quite a lot. Yeah, the thing is that there is no reasonable way to imagine the biharmonic Hardy space as some sort of combinations of analytic Hardy spaces. In the sense that, okay, apparently, oh, ouch, I think.
We can see that.
Okay.
We can see that.
Okay, can you see my tablet, the display?
I see something. You're scrolling now.
Ah, okay, yeah, because, yeah, okay, yeah, thank you. Yeah, internet connection is not the best right now. Right, so the thing is that somehow the virtue of one-dimensional magic, you know that L2 on R is just L2 on R plus L2 on R minus, in some sense. So H2, okay, L2 on the H2 harmonic on the unit disk is just usual H2 plus H2 bar. So for the one-dimensional scenario, you can clearly decompose your harmonic H2 space into some of analytic and anti-analytic parts, which unfortunately cannot happen in the BiDisk case, because your anti-analytic part just reflects your upper right quadrant to the lower left quadrant, and the other remain unhandled. So this is somewhat of a problem. This where the actual analyticity comes into play, because there is nothing inherently analytical about this condition in the display, but we start with the spaces of analytic functions, and somehow in one-dimensional scenario this analyticity can be dealt with just because you can decompose the harmonic H2 into the sum of analytic and anti-analytic parts. But in two-dimensional scenario, when you live on the BiDisk, this is a bit of a problem. And generally, you cannot say that like H2 on the BiDisk plus its anti-analytic counterpart, and you have H2 harmonic, because you also have to add the like one half anti-analytic and another one half anti-analytic parts, and this you generally cannot really handle. So this is the problem. And again, if we go a little bit lower, then I can say that for the case of the classical Dirichlet space, we managed to prove the exact analog of the one-dimensional result. That is, if okay, can you see me scrolling, or is it stuck?
In this moment, it's stuck. But
yeah, unfortunately, yeah, the internet connection on my tablet is somehow very bad right now. But okay, let me just wait until it. Yeah, I think I moved to where I want. So we managed to show an if and only if condition for the Dirichlet space on the BiDisk, for the unweighted Dirichlet space on the BiDisk. And this is stated in a slightly different way, but nonetheless, measure mu on the BiDisk is Carlson for the Dirichlet space, if and only if you have the complete analog of one-dimensional result. And despite of this thing being complete analog of one-dimensional result, alas, the internal workings here are much more complicated due to two reasons. Well, first reason that some magic happens, which allows us to forget about analyticity. So there is a certain reproducing kernel trick which says that the real part of two reproducing kernels, kz1 times kz2, is somehow equivalent to the real parts, to the products of the real parts. And this is something that happens, unfortunately, very rarely, because the real part of the product of two analytic functions is not exactly the product of the real parts. Nonetheless, in this case, it is kind of true. So this is the very unnatural thing that is very convenient for us, because it happens with the Dirichlet space on the BiDisk. And the second part is that combinatorial results on the bitree. So the same combinatorial argument that can be used to prove anything in dimension 1 can, again by some magic, be extended to the proof of the result on on the bitree of the product of two trees. However, the thing is that let me write this in the huge block red letters. But as of now, not on the product of try of, well, let's see, of 4 trees and higher. So again, there is some not yet understood magic that allows us to deal with the product of 3 trees, but if you have 4 trees and higher, so if you are trying to extend the results to the proper polydisk, something that we don't yet know happens that not exactly forbids us from obtaining this result, but we have to investigate this whole business further and further. So strangely enough, there is some very unusual magic happening actually twice. So first of all, we can go from the analytic case to the harmonic case by magic number 1, and we can go from the harmonic case to the discrete case and deal with the discrete case for the dimension 2 and probably 3, but not for the dimension 4 or higher. So actually there are 2 kinds of problems. One is how to get rid of analyticity, and the other one is how to get higher dimensions. And for instance, if I go back a little bit higher to this theorem by Chang and Hefferman here, where I say that this is true for biharmonic functions but not for analytic functions. There is an argument that says these things would be actually equivalent here if we use the famous, so this equivalence goes by Lacey Ferguson paper about the about the multipliers of about the Hardy space on the bidisk. So as of now, Sasha Wolberg found some kind of a Leakian argument there, and we think that okay, the result itself might be true, but the way it's written, the way it's proved, might have some holes, which we don't see how to fix yet. So there's that. And for the weighted case scenario. For the weighted case scenario, we know the same theorem. We would know the same theorem for also true for any a b strictly greater than 0. Well, it's less or equal than 1. But again, for harmonic functions. That is, this magic which happens for the unweighted Dirichlet space stops happening when we move to the weighted scenario, and then we can only use we can only prove that the measure is Carlson for the harmonic for the space that consists of harmonic functions, which of course is much larger than the space of analytic functions. And in my opinion, that's quite an interesting question by itself. Do the Carlson measures for the weighted Dirichlet spaces for harmonic functions and analytic functions coincide, or is can it happen that the measure is Dirichlet for the small Carlson for the smaller analytic version of the space, but is not Carlson for the larger harmonic version of the space? I mean, what we can see points in the direction of the total equivalence. So for any a and b between 0 and 1, the Carlson measures, the sets of Carlson measures coincide, but we can only show again this for one endpoint of the scale when a is b is 1 for the Dirichlet case, and based on the Lacey-Ferguson argument for the other endpoint of the scale where a is b is 0. And anything in between, it is sort of a mystery, just because the reproduction kernel trick kind of stops happening there. Right. So again, this, in my opinion, this by itself is quite an interesting question, and unfortunately, I don't think we have theory of Hankel operators for the weighted Dirichlet space on the bi-disk. I mean, the situation in the two-dimensional case is, of course, much less known than usual. Okay, I guess I'm pretty much out of time now, and besides, this is the place where I would like to stop. So, disregarding all this thing, thank you so much.
Actually, thanks, Pavel. Actually, we are not. You are not. You're not short. you are.
Again, it was a nice place to stop, because otherwise I would have used another 10 minutes or so.
I think you just had another 10 minutes.
Alas.
Okay. Anyhow. Okay. So are there questions?
So maybe I have one just silly question. Is can you go just a little bit back to the slides? I think was the almost yeah. Okay. This so you have this kind of result for the bi-disk here, and there was a similar result for strongly pseudo-convex domain. Well, it was not probably exactly the same. Maybe Nicola knows better. This there is a result by Jasmine Raisi and Marco Abate and Alberto Saracco. So my question is, and there it's a kind of I mean, this seems to be more complicated from a geometrical point of view, because the bi-disk has many bad property with respect to strongly pseudo-convex domain. So my question is, do you think that this kind of result are completely they completely ignore the geometry of the domain? So you might have also similar result, let's say, for finite type domains or other kind of domains, or it's really two different ways and to prove them?
No, I think the geometry of this particular domain of the bi-disk here is quite important, because the way we prove things is actually we do pretty much the discretization of the unit disk by the tree, the usual Whitney thing, and then we multiply it Cartesianly by itself. So you get a very specific thing. I think if you can do the discretization, well, I mean, if the thing is that somehow, again, another part of magic that happens here, that you can move from the continuous setting to the discrete setting without losing much. And I don't know if it can happen when you are discretizing more general domains. I mean, I try to think about it, but I don't know. And in particular, we managed to do what we managed to do just because the unit disk is such a nice thing that even if you take a product of those, you still get nice object, geometrically speaking. Well, maybe it's not so nice, but it retains some of its properties, discrete-wise at least, so we can make similar stuff to happen. I mean, for that, to properly answer the question, I would have to know how the possible discretization of a nasty domain would look like. And of course, if you can move between continuous and discrete scenarios. Here it is done by the virtue, again, of some magical trick with the reproduction kernels.
Okay, thank you.
Alexandro?
Yeah, can I ask
Alexandro?
you, I'm just curious about this Chang-Fefferman theorem. So this was stated for the biharmonic space, right?
Yeah, so far as I can tell, yeah, for biharmonic space.
Because I'm just curious about this connection with the gap in Lacy-Ferguson. So you mean if what should hold?
Well, okay, so for this, this you probably should ask Sasha about, because it was him who found, well, maybe it's not a gap, maybe there is a part of Lacey Ferguson's paper that is written in such a way that we cannot understand it, really.
Ah, okay, yeah.
Yeah, so this is a gap in quotes, so to say. But I mean, I think he wrote to Lacey, and he did not explain yet how to understand this particular piece. But I think there is a certain way that you can use Lacey-Ferguson theorem to say that the analytic and the bianalytic and biharmonic cases are all one and the same. Yeah, you cook up some symbol for a Hankel operator, and then by magic of, okay, you say that it is bounded if and only if this thing satisfies some conditions, and these conditions, they don't really see the difference between analytic and harmonic case. Basically, you just use this Lacey-Ferguson theorem and go to town with that.
I see. Thank you. Yeah.
Unfortunately, this works only for the Hardy case scenario. And if your space is weighted, yeah, we don't know how to proceed.
Yeah, sure. No, I was just curious. But yeah, thanks.
I have a probably silly question, may I? Hi, Pavel.
Yeah.
So let me stick the question to the 1D case. So do you think it makes any sense to consider the same problem, so that of characterizing the measures for the Hardy inequalities on metric trees? By this I mean like a tree on which you don't just jump from a vertex to the other, but you can also walk along edges, so that edges are sort of copies of intervals, and so also functions that take different values along edges. So in this sense, I mean, if you take the original Hardy operator on R, I mean, what happens if you skip the discretization from R to natural numbers? Like construct a tree so that, like, if you restrict to a geodesic, now is a copy of R and not of.
Come to think, well, never thought of that. I guess, I mean, as long as you have a directed graph without directed cycles type object, I mean, with a metric on it or whatever, at least the whole potential theory holds. So I guess, yeah, could possibly be reasonable, but I never really considered non-discrete scenarios. So however, that, I guess, I think you can emulate this thing by adjusting the weight W, which is attached to the tree. Well, maybe not to the most generality, but I think you can. But yeah, okay, yeah, I think you can do this on the metric trees, but well, I don't know much about those.
Okay.
May I add something to concerning Filippo's question? I think you compare a situation of a strongly pseudo-convex domain, say the ball, right? With the complication here is that you really have a product, and so you have rectangles with two different parameters, and they can be the two sizes can be of quite different one from the other in size. And that, I mean, I don't know the paper you mentioned by Saracco and others, but I suppose there, for instance, they only have tens over balls on the boundary. Nothing like two-parameter objects like rectangles. So
I completely agree that this case, I think, is more complicated.
That's where all the complications and I mean, in the Chang-Pfefferman work, for instance, they come from the fact that you have this. So from the geometric point of view, what probably matters is not so much the dimension, but what may be the rank if you are in symmetric domains, right? That the ball in any complex dimension is a symmetric domain of rank 1. And whereas the bidisk has rank 2, and that determines the parameters that you have in the defining what are the natural objects considers whether you have just balls or rectangles. I think that's the complication of this case.
Yes, but actually, yeah, any kind of complex ball has a nice. I mean, if it is a ball, it has a nice discrete approximation, and then it would work pretty much the same way. Instead of dyadic tree, you use whatever p-adic tree you would like to have. And still, I mean, for instance, it translates to the fact that you have unique geodesics between two vertices, and that would be still true for any for the ball of any dimensions, for any dimension really. And but if you have some less more complicated domain, then you would still have to get a nice discretization of that and still pass from discrete to continuous case. So I'm working basically with disks or balls. I mean, you can have this on polyballs. The very same thing.
In fact, for the bidisk, what you take as the boundary is the Shiloh boundary, which is which has codimension 2 in this case, right?
Yeah.
Codimension 1. That's an indication of that there are big differences and big complications because of this kind of higher rank.
Yes, and also, I mean, I would also like to stress once more that, again, through some magic, which we still don't understand, we still have the same result on the tri-disk, but not on the 4-disk. And for my money, it would be very nice if things somehow would fail for the 4-disk. But I think it works all the same in any dimension for any polydisk. But still, it would be quite interesting if the things start to fail after dimension 4.
For me, a remark, I find it very interesting, this interpretation in terms of symmetric spaces. Never thought about it. I hope there will be a chance to talk about this.
I mean, I suppose.
Oh no, Fulvio?
I mean, I suppose as soon as you take, for instance, the product of two spheres or two balls, say, in higher dimension, you run into the same kind of problems.
Right, which is.
I
think in the early times, right? In the early times of harmonic analysis, it was the problem dealing with the rectangles of these articles of Zygmunt and others in the 30s. One of the problems is that, by this, there is not one geometry. There is a one parameter family of geometries. Right, Pavel? That's pretty much. And, while in the ball and I guess also in pseudo-convex domains, you have one natural geometry. Maybe more complicated, maybe less complicated, but it's one. On the bidisk, there is not one. I think that even things like measures are more difficult to understand in the bidisk case.
Oh yeah, yeah. There is a natural extension of the Hausdorff measure to the biparameter case, which we don't understand much of it really. So, for instance, Frossman's lemma is kind of known for that particular case.
Okay, are there other questions, remarks? Okay, well, let's thank Pavel again, and we'll be happy for